Great. So as you remember, last week you started planning an investigation to work out exactly how much limestone was in 3 different rock samples, so you could say which one had the most limestone and which one had the least. Now, as I feared, some of you are very rusty on exactly how to plan, write up and do practical designs. So we're going to take another week, and this time you are going to improve the plan that you submitted to me last week. For some of you there will be very little work to do, and actually you're going to have a much shorter lesson than last week. For those of you who didn't spend the full hour last week, you've got a lot more to do this week. So basically, how much you did last week controls how much you've got to do this week. Starting off with the variables, you had to identify the independent variable, the dependent variable, and some control variables. And here is an example from your class. My independent variable is the limestone. Well, what about the limestone? The colour of the limestone, the name of the limestone, the mass of the limestone, the smell of the limestone. I compared a limestone that smelled like gorgonzola with a limestone that smelled like ML towel. You know, what exactly about the limestone was your independent variable? The dependent variable, as I said in the video, is not the amount of carbonate in each limestone. You are not Spock. You don't have a tricorder that you can point at your limestone and say that one contains exactly 75% carbonate and that one contains 20% carbonate. You don't have that. What are you actually measuring in your experiment? This person did, however, come up with good control variables. The volume of the acid, the type of the acid, the temperature of the reaction mixture. They are good control variables. But this was the method. Could you do this if I gave you this method? Set up the apparatus as shown in the diagram below, get 3 small dishes of acid, put the limestone in the acid dish, and whichever one has the highest volume of salt at the end will be the one with the most carbonate. If I gave you that and a lesson, could you do the practical? I very much doubt it. And many of your methods were like this, just nowhere near enough detail to say to another student in another class how you would actually do the experiment. If you're not sure, give the methods to your parents and see if they understand what to do. And if they don't, it's not good enough. Here's a method that sounds great. Get a gas syringe, support it with a stand boss and clamp using a measuring cylinder, add 50 centimetres cubed of dilute hydrochloric acid to a conical flask. Add 0.4 grams of calcium carbonate, immediately connect the gas syringe and start a stop clock. Sounds great, doesn't it? Every 10 seconds record the volume of gas produced. When the reaction is complete, clean the apparatus as directed by a teacher and repeat steps 1 to 5 with different concentrations of hydrochloric acid. Well, it sounds great, but then why are we timing this reaction? Why are we changing the amount of acid? Actually, it's really clear that this person has just got any old method off the internet, and it's not going to do anything. If this person could explain to me how this is going to tell you the amount of limestone in a particular sample of rock, brilliant, but I cannot see how this method is appropriate for the investigation we're doing. So you've got to think about your work. You can't just get something off the internet and hope it's the right method. So this person has clearly just copied a method off the internet without thinking about whether it answers the question. Here's another example, and this one is much better. My independent variable is the type of limestone. Good. We're being specific here. Not the mass, not the colour, not the smell, the type of limestone. The dependent variable, how much carbon dioxide is made. Brilliant. That's what you can measure. You can measure the amount of carbon dioxide being made. Control variables. the same amount of acid, we've seen that before, but the same amount of limestone. Of course, it's really important that you start with the same mass each time. These are good variables. Another example below contains a fairly good method. First, weigh your limestone rock and write down the weight. Crush up your limestone rock and put it in a boiling tube. Set up the apparatus as shown in the diagrams below. Heat the boiling tube with your crushed limestone on a roaring blue flame. After 5 minutes, take it off the heat and weigh what's left. I'm following you so far. Then take the number from the beginning and subtract the number you just got. You've lost me. This last bit, do you understand what it means? Take the number from the beginning, subtract the number you just got from it. Even if you understand that, how does that help you answer the question of how much limestone is in the rock? So it is a good start to the method. It does lack detail. For example, how much limestone should you use? A gram, a kilogram, a ton? Let's be a little bit more specific when we write our methods. Here's a good method that actually does answer the question. Again, we haven't got an independent variable that's particularly helpful, the limestone, but the dependent variable's okay. The amount of carbon dioxide produced, that's good. Control variables, amount of limestone, amount of hydrochloric acid, temperature of the acid, these are all good control variables. Set up at the apparatus as shown in the diagram below. Add 50 centimetres cubed of hydrochloric acid to the conical flask. Add 10 centimetres cubed of water to the measuring cylinder and take note of where it comes up to. Add 10 grams of limestone to the beaker, wait for 5 minutes. Measure the increase in volume using the measuring cylinder. Also use universal indicator to measure the acidity of the solution. I'm not sure about this. I'm not sure why that's necessary. That isn't explained anywhere. But the rest of it I understand. And then we've got repeat for all 3 limestone samples. This is a good method. Now let's look at the diagrams. And this is our first effort. Of all the people that actually submitted the work, this was the most pathetic. This is the entire total of one person's work. No variables, no method, the diagrams not even drawn with a ruler or labelled. And if I gave you this, would you be able to work out anything about this practical? I seriously doubt it. Some people clearly did submit some work, but in some cases it was far too blurry for me to actually read what was going on. And the one on the right isn't even the correct way round. I cannot rotate the PDFs in Google Classroom. If they are submitted on their side, I would have to mark them on their side. I'm not prepared to do that. So do make sure when you submit your work, it is actually submitted in the correct orientation and not blurry. This diagram's getting better. At least I can read it. At least it is partially labelled. The CO2 emitted by the acid and carbonate in the rocks reacting to each other is funneled through the lime water, which will turn whiter the more CO2 there is. And if there's more carbonate, the lime water will be milkier. It's a great idea. But don't use Word to do your diagrams. Draw them properly on a piece of paper with a pencil and ruler. Take a photo and just put them into your Word document. Or just do the whole thing on lined paper and then take a photo of that. But don't use Word for diagrams. Also, don't draw pictures. I love the attempt here. It's pretty, but it's not a scientific diagram. This is a drawing that someone has done. We want proper scientific diagrams. I even gave you a list of how to draw these things attached to your last homework. It is clear that many of you have not looked at that. You didn't listen to me in the video, you didn't pay attention to what was required of you, and now you're going to have to do it again because you didn't do it right first time. Some people did listen. This is a better example, although one thing to note, look at this. If you look at a glass of water from the side, is it really like that? If it is, it's probably because you've just knocked into the table. If you look at a glass of water from the side, the water level is absolutely flat. And this is how it should be drawn in scientific diagrams. We've got an evaporating basin, the liquid level would be flat. It's also not labelled. A scientific diagram needs to be labelled. Here's two scientific diagrams that are getting better, but they should be drawn with a ruler. Don't draw them freehand. You need to draw them with a ruler where appropriate. And almost all of this can be done with straight lines, not freehand. Here we go, getting much better here. We've got some nice scientific diagrams, clearly drawn with a ruler where possible. Look at this. A ruler's been used to draw the sides of the test tube, and then the bottom's been completed freehand. Great. We've got the bungs with the hole in them, which is really important. So the bungs here, the gas can actually get through, although I am a bit worried that the system on the right might explode. There's nowhere for the gas to escape to, and so the pressure is going to build up. Bottom left, again, a beautiful diagram drawn with a pencil and ruler and labelled, but we need the tube to go through the stopper here. We also need the tube on the right hand side to go into the lime water, because otherwise the gas is not going to go into the lime water and turn it cloudy. And as it was drawn, that would probably have exploded too, because it was a sealed container producing a gas. But these are good diagrams. Some of you were really stuck, and I think it's because probably you've never been asked to think how to do a practical. You should have done the rock salt practical in year 7. You should have planned that yourself, but it may be that you never got the chance to do this, and so you actually haven't had to think before about how to do a particular practical yourself. But that is the skill we're testing. That is why we're doing this. It's so you get practice of that skill and planning your own investigation rather than just being spoon-fed about what to do. So here are the methods that people suggested, and they were all workable methods. So the first method was several people said, well, I'm going to work out the amount of salt produced by the reaction. Now the only problem here was that you had to separate the salt produced from anything else that was there in the reaction beaker. A method might go like this. React the crushed rock with an acid, filter out any unreacted rock, evaporate the water, see how much salt is left. More salt equals more limestone. So we've got rid of any unreacted rock by filtering it. The problem is you're going to have acid left over in that reaction mixture. Where's that going to go? Is that going to be left in the evaporating dish when you evaporate out the water? So if you use this method, you've got to think how you're going to make sure that you're not left with any acid in the evaporating dish at the end. Acid doesn't evaporate, in case you're wondering. A second method that was very workable is the mass lost from the flask. So people worked out, and this is what I was trying to guide you towards, that the reaction gives off carbon dioxide gas. So you react the crushed rock with an acid, you weigh the container and the contents at the start, you weigh the container and the contents when the reaction is over, and the mass difference tells you the mass of carbon dioxide that escaped. So if your reactants, or if your reaction weighs 2 grams less at the end, 2 grams of carbon dioxide gas have escaped. More carbon dioxide means more limestone. This was a good method. Several people suggested it. Another one that was fairly common, again, people realising that the reaction is giving off carbon dioxide, was using lime water to test for it. So react the crushed rock with an acid, bubble any gas produced through lime water. However, most people then said, time, how long it takes for lime water to go cloudy. And I presume that they meant that the shorter time it takes, the more limestone there is. But the danger here is actually you're not measuring the amount of limestone in the rock, you're just measuring how fast that limestone reacts. So it may be that another sample reacts slower but has more limestone, and your experiment, if you did this, won't detect that. It will just detect which limestone reacts fastest. So you're going to have to come up with a method that makes sure you're measuring the amount of limestone and not just how fast it reacts. The fourth method, and this is the one that I pointed you to the hint for, is that you measure the amount of gas produced, either the mass of the gas produced or the volume of the gas produced. So you react the crushed rock with an acid and you collect the gas that was produced. The easiest way is in a gas syringe. You literally have a tube going into a syringe that fills up with gas. Or, and this is what we do at GCSE, you collect it over water in a measuring cylinder. And this is the practical method that I was trying to lead you towards, which is you have a measuring cylinder that's full of water, and the gas that is produced bubbles up and starts filling the measuring cylinder, and you can just read off the measuring cylinder the volume of gas you collected. The more carbon dioxide that is produced, the more limestone. Many of you didn't get onto the risk assessments, but there were lots of not so good risk assessments. So a lot of carbon dioxide could suffocate you, that is certainly true, but not the volumes that you are producing in this experiment. Glass could break, so it would be sharp. Good, broken glass is good, but just saying be cautious when handling the glassware, this is not a good precaution. Because any sensible student would be cautious when handling the glassware. What can they do to prevent it breaking, or what could they do once it's broken? So you could say things like keep glassware in the middle of the bench, or things like clean up broken glass immediately with dustpan and brush. These are much better precautions. The next one, just one hazard here, inhaling CO2, low risk, seal the beaker. Well, by sealing the beaker, aren't you increasing the risk of the beaker exploding? So actually what you've done is you've turned a low risk hazard into a much higher risk hazard by sealing the beaker. So do be careful. But there were people who came up with three good hazards and precautions. Boiling water spilling on you, stand up so you can get out the way quickly. And these are people who said that they were going to heat the acid. Smashing glass, clear up anything that's broken. Knocking the Bunsen over, set it up in the middle of the desk. Hot calcium carbonate could still be hot and could burn you. This was the person who thought that they were going to heat it and release the carbon dioxide, used tongs to pick up the tubes. These are sensible precautions. Just make sure they are appropriate for your investigation. So what do you need to do this week? Improve or redo your variables to be specific if you haven't done it. Improve or redo your method to be usable and to include details, for example, how much rock to do. Feel free to just add bits in pencil if you have done a good job first time round. Improve or redo your diagram to be drawn in pencil with a ruler in 2D and fully labelled. Improve or redo your risk assessment to give 3 likely hazards with suitable precautions. Some of you have done most of that already and will have very little work to do. Some of you have hardly done anything and are going to have a much longer lesson to this time. Finally, draw a results table with appropriate headings and units that you can use to collect your results based on your experiment, and prepare your graph remembering splat. This time you will be graded on your submission. So when you upload it to Google Classroom, there will be a rubric. The rubric will tell you exactly how you're going to be marked, and that will be useful for you to check that you've done everything you need to. Don't forget to submit it by the end of the lesson if you can. Certainly by the end of the day. Goodbye.